In the last segment, we defined authenticated encryption, but I didn't really show you why authenticated encryption is the right notion of security. In this segment, I want to show you that authenticated encryption, in fact, is a very natural notion of security, and I'll do it by showing you that it defends against a very powerful attack called a chosen ciphertext attack. So in fact, we already saw a number of examples of a chosen ciphertext attack. So imagine the adversary has some ciphertext seed that it wants to decrypt. And what it can do is, for example, fool the decryption server into decrypting some ciphertext, but not actually the ciphertext seed. So we already saw some examples of that. If you remember in the first segment, we looked at an adversary that can submit arbitrary ciphertext, and if the plaintext happened to start with destination equals 25, then the adversary is actually given the plaintext in the clear. So that's an example of an adversary that can obtain the decryption of certain ciphertexts, but not all ciphertexts. Another example we saw is an adversary that can learn something about the plaintext by submitting ciphertexts to the decryptor. So we had this example where the adversary submits encrypted TCP/IP packets to the decryption server, and if the decryption server sends back an ACK, the adversary learns that the decrypted plaintext had a valid checksum, and otherwise the decrypted plaintext didn't have a valid checksum. So this is again an example of a chosen ciphertext attack where the attacker submits ciphertext and learns something about the decryption of that ciphertext. So to address this type of threat, we're going to define a very general notion of security called chosen ciphertext security. So here we're going to give the adversary a lot of power. Okay, so he can do both chosen plaintext attack and a chosen ciphertext attack. In other words, he can obtain the encryption of arbitrary messages of his choice, and he can decrypt any ciphertext of his choice other than some challenged ciphertext. And as I showed you before, this is actually a fairly conservative modeling of real life. In real life, often the attacker can fool the decryptor into decrypting certain ciphertext for the attacker, but not all ciphertexts. So the model here is that the attacker has a certain ciphertext that it wants to decrypt. It can interact with the decryptor by issuing these chosen ciphertext queries to the decryptor, namely to decrypt various ciphertext other than the challenged ciphertext. And then the adversary's goal is to break semantic security of the challenged ciphertext. So you notice that we're giving the adversary a lot of power, and all we're asking him to do is break semantic security. So it's going to be fairly difficult to design systems that are secure against such adversaries, and nevertheless we're going to do it. So let's define the chosen ciphertext security model more precisely. So as usual, we have a cipher ED, and we're going to define two experiments, experiment 0 and experiment 1. So this should look somewhat familiar by now. The challenger is going to start off by choosing a random key, and now the adversary is going to submit queries to this challenger. Every query can be one of two types. It can be a chosen plaintext query, or it can be a chosen ciphertext query. So chosen plaintext queries, we already know, basically the adversary submits two messages, M0 and M1. They have to be the same length, and the adversary receives the encryption of either M0 if we're in experiment 0, or M1 if we're in experiment 1. So he receives the encryption of the left or the right, depending on whether we're in experiment 0 or in experiment 1. The second type of query is the more interesting one. This is where the adversary submits an arbitrary ciphertext of his choice, and what he gets back is the decryption of that ciphertext. So you notice the adversary is allowed to decrypt arbitrary ciphertext of his choice. The only restriction is that the ciphertext is not one of the ciphertexts that were obtained as a result of a CPA query. And of course, this wouldn't be fair otherwise, because the attacker can simply take one ciphertext that was obtained from a CPA query. That's going to be either the encryption of M0 or the encryption of M1. If he could submit a CCA query for that particular ciphertext, he will, in response, either obtain M0 or M1, and then he'll know whether he's in experiment 0 or in experiment 1. So this wouldn't be fair, so we say that these CPA ciphertexts that he received are the challenged ciphertexts, and he's allowed to decrypt any ciphertext of his choice other than these challenged ciphertexts. And as usual, his goal is to determine whether he's in experiment 0 or in experiment 1. So I'm going to emphasize again that this is an extremely powerful adversary, one that can decrypt any ciphertext of his choice other than the challenged ciphertext, and still he can't distinguish whether he's in experiment 0 or in experiment 1. So as usual, we say that the cipher is CCA secure, chosen ciphertext secure, if the adversary behaves the same in experiment 0 as it does in experiment 1, namely cannot distinguish the two experiments. So let's start with a simple example and show that in fact CBC with a random IV is not CCA secure, is not secure against chosen ciphertext attacks. So let's see why that's the case. So what the adversary is going to start by doing, he's going to simply submit two distinct messages, M0 and M1, and let's just pretend that these messages are one block messages. And what he's going to get back is the CBC encryption of either M0 or M1. You notice the ciphertext only has one block because the plaintexts were only one block long. Now what is the attacker going to do? Well, he's going to modify the ciphertext C that he was given into C prime simply by changing the IV. Okay, so he just takes the IV and XORs it with 1. That's it. This gives a new ciphertext, C prime, which is different from C, and as a result, it's perfectly valid for the adversary to submit C prime as a chosen ciphertext query. So he asks the challenger, please decrypt this C prime for me. The challenger, because C prime is not equal to C, must decrypt C prime. And now let's see, what happens when he decrypts C prime? Well, what's the decryption of C prime? Let me ask you. So you probably remember from the first segment that if we XOR the IV by 1, that simply XORs the plaintext by 1. So now the adversary received M0 XOR 1 or M1 XOR 1, and now he can perfectly tell whether he's in experiment 0 or in experiment 1. So the advantage of this adversary is basically 1, because he can very easily tell which experiment he's in, and as a result he can win the chosen ciphertext security game. So if you think about it for a second, you'll see that this attack game exactly captured the first active attack that we saw, where the adversary slightly changed the ciphertext that he was given, and then he got the decryptor to decrypt it for him, and therefore he was able to eavesdrop on messages that were not intended for the adversary. So I want to emphasize again that this chosen ciphertext game really does come up in real life, where the adversary can submit ciphertext to the decryptor, and the decryptor can reveal information about the plaintext, or can give the plaintext outright to the adversary for certain ciphertext, but not others. So this is a very natural notion of security, and the question is, how do we design crypto systems that are CCA secure? So I claim that this authenticated encryption notion that we defined before actually implies chosen ciphertext security, and this is why authenticated encryption is such a natural concept. Okay, so the theorem basically says, well, if you give me a cipher that provides authenticated encryption, the cipher can withstand chosen ciphertext attacks. And more precisely, the theorem says the following: if we have an adversary that issues Q queries, in other words, at most Q CPA queries and Q chosen ciphertext queries, then there are two efficient adversaries, B1 and B2, that satisfy this inequality here. So since the scheme has authenticated encryption, we know that this quantity is negligible because it's CPA secure, and we know that this quantity is negligible because the encryption scheme has ciphertext integrity. And as a result, since both terms are negligible, we know that adversary's advantage in winning the CCA game is also negligible. So let's prove this theorem. It's actually a very simple theorem to prove. And so let's just do it as proof by pictures. Okay, so here we have two copies of the CCA game. So this would be experiment 0, and the bottom one is experiment 1. You can see the adversary is issuing CPA queries, and he's issuing CCA queries, and at the end he outputs, a certain guess B, let's call it B prime, and our goal is to show that this B prime is indistinguishable in both cases. In other words, the probability that B prime is equal to 1 in the top game is the same as the probability that B prime is equal to 1 in the bottom game. Okay, so the way we're going to do it is the following. Well, first of all, we're going to change the challenger a little bit so that instead of actually outputting the decryption of CCA queries, the challenger is just going to always output bottom. So every time the adversary submits a CCA query, the challenger says bottom. And I claim that these two games are in fact indistinguishable. In other words, the adversary can't distinguish these two games for the simple reason that because the scheme has ciphertext integrity, the adversary simply cannot create a ciphertext that's not in C1 to Ci-1 that decrypts to anything other than bottom. That is the definition of ciphertext integrity. And as a result, again, because of ciphertext integrity, it must be the case that every chosen ciphertext query that the adversary issues results in bottom. If the adversary, in fact, could distinguish between the left game and the right game, that would mean that at some point he issued a query that decrypted to something other than bottom, and that we could use to then break ciphertext integrity of the scheme. And since the scheme has ciphertext integrity, these left and right games are indistinguishable. Okay, so that's kind of a cute argument that shows that it's very easy to respond to chosen ciphertext queries when you have ciphertext integrity. And the same thing exactly applies on the bottom, where we can simply replace the chosen ciphertext responses by just always saying bottom. Okay, very good. But now, since the chosen ciphertext queries always respond in the same way, they're not giving the adversary any information. The adversary always knows that we're always going to just respond with bottom. So we might as well just remove these queries because they don't contribute any information to the adversary. But now, once we remove these queries, the resulting game should look fairly familiar. The top right game and the top bottom game are basically the two games that come up in the definition of CPA security. And as a result, because the scheme is CPA secure, we know that the adversary can't distinguish the top from the bottom. And so now, by this chain of reasoning, we've proven that all these games are equivalent, and in particular, the original two games that we started with are also equivalent, and therefore, the adversary can't distinguish the top left from the bottom left, and therefore, the scheme is CCA secure. So this gives you the intuition as to why authenticated encryption is such a cool concept, because primarily it implies security against chosen ciphertext attacks. Okay, so as we said, authenticated encryption ensures confidentiality, even if the adversary can decrypt a subset of the ciphertext. And more generally, even if he can mount a general chosen ciphertext attack, he still is not going to be able to break semantic security of the system. However, it is important to remember the two limitations. First of all, it does not prevent replay attacks on its own. We're going to have to do something in addition to defend against replay attacks. We're going to see several examples where if the decryption engine reveals more information about why a ciphertext is rejected, it doesn't just output bottom, but it actually outputs more information, say by timing attacks, and that explains why the ciphertext is rejected, then in fact that can completely destroy security of the authenticated encryption system. So we'll see some cute attacks like this in a later segment. Okay, so in the next segment we're going to turn to constructing authenticated encryption systems.